Hey everyone, and welcome to The Explainer. Today, we are pulling back the curtain on the real brains behind modern AI, neural networks. We're going to break down what they are, how they actually work, and why they've become so incredibly important in everything from your smartphone to self-driving cars.
So take a look at this. Your brain, it knows what this is instantly, right? It's a messy, maybe poorly written number, but you get it. Now imagine trying to write a computer program, a set of rigid if-then rules to do that same job. It's almost impossible. So how in the world do we teach a machine to see and learn more like we do?
Well, the answer comes from taking a page out of our own biology. Instead of programming with rigid rules, we build a learning machine, a system that isn't told what to do, but has the ability to learn from experience, kind of like our own brains. And that brings us to the core idea itself, the neural network. Now, let's be clear, this is not a literal biological brain in a box. It's a computing system inspired by the brain. It's made up of these interconnected little processors, we call them neurons, and they're all organized in layers. And their whole job is to find patterns in data and, well, learn from it. Okay, so let's really get into the nuts and bolts. To understand this, let's imagine we're building a simple network to solve that handwritten number problem. How does it possibly go from just a grid of pixels to a confident prediction like, yep, that's a 9? So information basically flows through three main stages. First, you've got the input layer. Think of it like the retina of the eye. It just sees the image with one neuron lighting up for every single pixel. Then that information gets passed to the hidden layers in the middle. This is where the real magic, the heavy lifting happens. And finally, you have the output layer, which makes the final call. It has 10 neurons, one for each number from 0 to 9, and whichever one lights up the brightest, that's the network's final answer. So, what's the big idea here? What are we hoping these hidden layers are actually learning to do? Well, the hope is that they're building up understanding in layers of abstraction. The first hidden layer might just learn to spot simple things, like little edges from the raw pixels. Then, the next layer might learn how to combine those edges into more complex patterns, like loops or straight lines. And then, finally, the output layer takes those patterns and puts them together to identify the whole digit. And here's the kind of crazy part. Each one of those neurons is just a tiny, simple calculator. That's it. It gets signals from the layer before it, it multiplies them by a weight to decide how important they are, it adds a little number called a bias to kind of nudge the result, and then it spits out its own signal. The learning part is just the process of tweaking all those weights and biases until it gets the right answer. And this number right here, this shows you the sheer scale we're talking about. For our simple little network that just recognizes digits, learning means finding the perfect setting for over 13,000 of those little knobs, those weights and biases. It's a massive optimization problem. Now, that basic structure is really just the beginning, because just like you wouldn't use a hammer to fix a watch, not all neural networks are built the same. Different problems require totally different designs, or what we call architectures.
First up, we've got the undisputed champion of anything visual, the convolutional neural network, or CNN for short. This is the architecture that basically gives machines the power of sight.
CNNs work by scanning an image with tiny little filters that are designed to look for simple features, like edges or corners or textures. Then, just like our digit recognizer, deeper layers combine those simple features into more and more complex objects. This is the tech behind Face Unlock on your phone, how a Tesla sees a stop sign, and even how AI helps doctors spot tumors in X-rays. Okay, so images are one thing, but what about data where the order of things is everything, like language or a piece of music? For that, we turn to the recurrent neural network, or RNN, and they brought a game-changing idea to the table: memory. RNNs use this clever little feedback loop that lets them hold on to information from the previous step. It gives them a kind of short-term memory. This makes them fantastic for anything in a sequence. Think about the predictive text on your phone. But they had a problem. Their memory was pretty short, so they struggled to keep track of context in really long sentences. And that limitation is what led to the next big breakthrough. And then, an architecture came along that just changed everything.
especially for understanding language. This was the transformer. See, an RNN reads a sentence one word at a time. A transformer looks at the entire sentence, or even a whole book, all at once. It uses this brilliant technique called an attention mechanism to figure out which words are the most important to every other word in the text. This gives it this incredible, deep understanding of context. And yes, this is the magic that powers all the big names you hear about today. ChatGPT, the latest Google Translate, and tools like GitHub Copilot that write computer code. So, we've gone through the what and the how. But to really get why this is all exploding right now, we need to take a quick look at the when.
What's really wild is that these core ideas are not new at all. Some of this stuff dates back to the 1940s. For decades, they were just too slow, and we didn't have enough data to make them useful. Everything changed around 2012. Suddenly, we had two things we never had before: massive amounts of data from the internet and powerful computer chips, like GPUs, that were finally fast enough to process it all. That moment kicked off the deep learning revolution we are living in right now.
And the impact has been, well, staggering. This technology is everywhere now, often working completely behind the scenes. It's helping diagnose diseases in healthcare. It's spotting fraud for your bank. It's the brain behind the recommendation engine on Netflix. And it's the vision system inside self-driving cars.
So after going through all these different types and seeing all these examples, what is the single most important thing to take away from all this?
It really boils down to this one powerful idea. AI isn't a magic wand. It's not a single hammer that you can use for every nail. It's a whole toolbox filled with very specialized tools. The real art and science of building great AI is knowing exactly which tool, which network architecture is the right one for the problem you're trying to solve.
And here's a quick cheat sheet for that toolbox. If your problem involves images or video, a CNN is almost certainly your go-to. If you're dealing with data that happens in a sequence, like text or speech, an RNN is a classic choice. But if you need a deep, nuanced understanding of language, right now, the transformer's king. Which leads us to one final huge question. We've managed to build these incredible tools that can see, remember, and even create in ways that mimic our own abilities. But as this tech keeps evolving at this insane pace, you just have to wonder, what problems are we going to build the next generation of tools to solve? And that's our look at the incredible world of neural networks. If you found this useful and want to dive even deeper into the tech that's shaping our world, please consider becoming a member. It helps us keep making explainers just like this one. Thanks so much for watching.